So this is our last week of classes, Tuesday, Thursday, and then next week will be the finals. And the nominal final date is that Tuesday, a week from today. But you can take the whole week to finish it if you need. I just have to turn grades in by the following Monday. So if I run into a time crunch with everybody turning stuff in late, I'm dating everything that comes in, date and timestamp. So I'm going to grade the first ones that come in first, and then if I run out of time, then you're out of luck. So the sooner you can turn something in, the better. There's a line forming. All right. So we've got 2 class periods to cover review topics for the final exam. And my first suggestion is that you go back and look through your old exams and look for weaknesses, places where if you know you made a mistake and it was what we would call a dumb mistake, and you know what to do, then you don't have to spend a lot of time on it. But if you find questions that you missed and you really don't understand why you missed them, you need to find out why, because those questions are there for a reason. Their approach is to cover basic topics and to find out if you know that material. And if you miss that question and you don't know why, then you don't know the material. So, and that's what the final exam is going to figure out. Did you learn from your mistakes? Also, the final exam is structured so that it's not in any order, not necessarily in any order of chapter. In other words, the final exam is all of first semester chemistry. So you could get things in different order. And that's the approach I'm going to take today. If nobody has any questions that they need to work on, then I'll just jump in. I've got this document where I've just compiled every question I can think of. And then I've gone through, because we don't have time to cover all of them. They're just too many. And I've got about 80 of them highlighted. And I'm going to just take them one at a time. They're not in any particular order. We may get through with them by the end of Thursday class, and we may not. If we don't get through with them by Thursday class, I have 2 options. Actually 3. I could just keep talking like I normally do, finish the recording and get them all done. Or we could come back for Thursday lab. And if you have lab questions, fine, show up at the very beginning. If there's nobody with lab questions, then you can show up and we'll use that lab time to finish the final exam discussion. And of course, the other option is, too bad, but that's not my nature. I want to cover all the topics and give you the best chance possible. Okay, so are there any particular problems that you've experienced in working toward the final exam? And I'll wait for a minute or so, and you can unmute and tell me if you do. If you don't, then we'll just jump right into it. Let's see, we still have 8. Okay. All right. So I'll probably spend most time, I should say it this way, I'll spend the least time on the last chapter we had an exam on, because that should still be fresh. We shouldn't have to spend a lot of time on that, although I might touch on it here and there, just to keep you on your toes. but we'll go back to the stuff that's sort of faded into the dark recesses of your mind and hit those early on and often to get your wheels turning. All right, so I'm going to share this document. If it's where I expect it to be, yeah, there it is. And share. All right. So I'm going to minimize this one on my end. You can't see what I'm doing, but I'm arranging things so that they look a little better. I think that should be large enough print that you can see the questions. And this document has over 300 questions in it, so obviously we're not going to get to all of them. But I tried to pick out ones that will really test your knowledge, to be honest. And they can't be, some of them can be specific, but you can't have too many of those where a lot of effort is required, because in a final exam, you've got to cover a lot of ground in little time. So that's just basic test-taking techniques to anticipate what the instructor is going to call on. Okay, so some of these are going to go fast. Some of them are going to take some time. So we'll just let the chips fall where they may. All right, for number one, which of the following is an example of a quantitative observation? That brings up the topic of the difference between quantitative versus qualitative. And the clues here are in the names. Quant refers to quantity. How much is there? It's measurable. So when you see quantitative, think numbers. A measurement has been made or will be made. Qualitative, on the other hand, is just it's a quality of something, like the solution turned blue. That would be a qualitative observation. So for number one, which of the following is an example of a quantitative observation? One, the piece of metal is longer than a piece of wood. It might require side-by-side comparison, but there's no measurement required. That's qualitative. Solution one is much darker than solution two. That's qualitative again. The liquid in beaker A is blue. Qualitative. The temperature of the liquid is 60 degrees centigrade. There you have the dimension, degrees centigrade, along with the magnitude of the observation, which is 60. 60 degrees centigrade is quantitative. All right. I heard somebody pop in. Let me see who it was. All right. I'll give everybody who shows up credit for being here. Okay. So, question 3. Which of the following has a different value on the moon compared to Earth? This requires that you know what's the basic difference between the Earth and the moon? Well, there are a number of differences, of course. We have an atmosphere and the moon doesn't. But the primary cause of all those differences is size. The Earth is much more massive than the moon. So will it have effect on such things as moles of something? No, moles is a count. Count, how much is it? It'll be the same on the moon and the Earth. Time. You could argue relativity with time. Large masses change the fabric of space-time, but for our purposes, time doesn't change on the Earth or the moon. Now you have the difference between mass and weight. Mass is a measure of how much substance there is. And that doesn't change no matter where you are in the universe. But the weight does. Weight is a measure of force. And force, in this context, is due to the difference in mass between the two objects. So the same mass on the Earth is drawn with greater force than that mass on the moon. So which of the following has a different value? Weight. All right. Now here's a reference to the periodic table. Should look like, let's see, where am I? Oh, okay, I got, there we go. So I can see what I'm doing. Periodic table. A major division of the periodic table is metals and nonmetals. And there are characteristics of metals that are different than nonmetals. So if you've got one characteristic for a metal, then the converse, or sometimes the opposite, will be true of nonmetals. So look at the division, and remember where the division is. Right? You start just under boron, and you start your zigzag. Go over, down one, over one, down one, over one, down one, over one, like that. And everything on the right is non-metal, everything on the left is metal. So what are the basic differences of the two? Well, metals are good conductors of heat. Non-metals are not. So in the context of this question, all of the following are characteristics. Poor conductor of heat. Yes, that's true. Brittle. Most non-metals are brittle. In other words, they crack easily. But metals are not brittle. Ductile. Non-metals are not ductile. Ductile refers to can you stretch it out into a long, thin dimension without breaking it. You can't do that with non-metals. You can with metals. You can pull them into very thin wires. Dull appearance. Most metals, pure metals, without corrosion on their surface, will be shiny, whereas non-metals will be dull. They will not reflect light very well. And non-metals tend to gain electrons in chemical reactions. That is true. Things on this side of the chart we know are more electronegative. They want to gain electrons, whereas metals want to lose electrons. Right, so there you have your basic difference between metals and non-metals. Now we're talking about naming compounds. So remember the rules for naming binary compounds. You have type 1, type 2, type 3. So what do you have with type 2 compounds? Actually, with type 1 and 2, excuse me, 1 compounds and 2 compounds. Metal and non-metal. So they're both alike in that respect. Metals with non-metals. Okay? So there must be a difference between 1 and 2. If you have metal and non-metal, the difference is the type 1 compounds, the metal has a fixed charge. It only has one possible charge. That's it. So that means the metals for type 1 compounds come from places in the periodic table where they can only have one charge. Alkaline metals, alkaline earths, and the boron family, down to about indium, first 4. After that, you're getting into variable territory. Those all have fixed charges, so they will be named with type 1 convention. The non-metal part, we have to have some conventions with charges for the non-metal part so that you can match, right? Because compounds that you don't see a charge on them have to be neutral. That means all the charges internally have to cancel. So we have certain conventions with nonmetals. Of course, the noble gases have a 0 charge. The halogens, in this context, have a -1 charge. The chalcogens, or the oxygen group, has a -2 charge. The nicogens would have a -3 charge. And then the carbon group is variable. So we don't work with that one too much. What about type 2s? Type 2 compounds are those in which the metal can have 2 or more different charges, depending on how it interacts with the nonmetal and the process that created it. So the metal could have 2 or more possible charges, not at the same time, but in this particular compound, the metal will have one of several different charges. Most of those metals come from the transitions, the transition metals in here. But you do have some down on this side that are not transition metals. And you have a periodic chart, just like this one, that will show you those charges. So when you name those compounds, you have to specify in the name the charge of the metal. And we do that with a Roman numeral. So let's go back to 7. We're not to 3. Well, we might as well cover it since we're here. Type 3 compounds are non-metal, non-metal. So we borrow from the type 1, type 2 convention for the non-metal naming. But instead of having to balance charges because they don't have charges, the non-metal nonmetals in type 3 compounds, we just say how many atoms are there in the molecule. We have those Greek prefixes: mono, di, tri, tetra, penta, hexa, hepta, nona, up to 10 possible, that we prefix the element's name to show how many there are. The only thing we don't do is we never say mono when it's for the left-hand partner in this compound. Okay, so let's go back to 7. The correct name for FeO. So the first thing you do is say, is it a type 1, 2, or a 3? It's a metal, non-metal. It's either a 1 or a 2. Then you differentiate. How about iron? Where does it come from? It's a transition metal, so it'll be a type 2. Now you have to figure out what the charge is. Oxygens are always 2 minuses. So if we have one of these and one of these, iron has to be 2+. No choice. So the name is iron 2 oxide. Okay. The correct name for calcium 2+. Where is the calcium? Let's see, we're getting feedback. We need to mute somebody. There we go. I think I got it. All right. So if you're going to name that ion, you're going to say ion at the end, right? And all these names that have ion are possible candidates. If you just say calcium, you're implying that that is the neutral element. So there's no charge. So that's why A cannot work. If it's an ion, we have to say ion. Now, where does calcium come from? It's an alkaline earth, which means its charge is always 2+, which means you don't have to say what the charge is. Okay? So the calcium 1, calcium 2 here, these two, they're out. That's redundant. It's excess that's not needed. We keep things simple. You don't say monocalcium ion either. Because when you say calcium and then ion, that tells you everything you need to know. It tells you the element, and it tells you whether it's an ion or not. And if it's an ion, then you look to see where it came from. How many charges, possible charges could it have? Only one. Under normal circumstances in a chemical reaction. Right. I know we've studied situations where we multiply ionize atoms. Those are special cases. We can drive more electrons off of a calcium 2+ ion, right? All you have to do is heat it up or hit it with ultraviolet radiation, and you can knock off more electrons, but that has nothing to do with naming convention or with normal behavior in chemical reactions. Calcium 2+ is the preferred charge for calcium. That's why B, calcium ion, says it all. Okay, so this one, let's see. Well, these pictures are used to answer 12, 13, and 14. And I know a lot of people missed these in the exam that had those in them. I can't remember whether it was the first one or the second exam. Anyway, what we're trying to do is to get you to think about the states of matter and the formation of compounds and what they would look like on the microscopic level. Right? We have macroscopic evidence, but in chemistry, we try to think on the microscopic level to explain the macroscopic. So in this case, we have microscopic pictures, and we look at them and we see that I think it's hard to tell with this first one. Let me blow it up just a little bit. Let's see, zoom, let's go to 200. Yeah, I think this first one does have different colored. So you've got one type, actually you've got a colored circle, a clear circle, and we've got some diamonds in there too, right? So what is unique about this, whatever it is? The particles in this container are very far apart, which should trigger in your mind gas. All right. Same thing for C. Those molecules are very far apart. That's a gas. Right. For B, they're very close together, so that should be, and they are arranged in a regular order, so that should mean solid. This one potentially could be a solid, amorphous solid, but it has different types of particles in it. Some of them are dark and some of them are light, but they're not arranged in a regular pattern. So that says to me liquid. And this one could be a gas, but we're also looking at mixtures, right? Do we have a mixture? You have two types of mixtures, remember, homogeneous mixtures, heterogeneous mixtures. So let's just take this first one and home in on it. Which best represents a homogeneous mixture of two elements? So we're implying with these diagrams, the elements are the single circles, diamonds, squares. That's an element. Right? So if you have a homogeneous mixture of two elements, which one fits? Well, you got to have elements first. C can't work because it's a compound. B can't work because it's pure, right? There's no mixture involved here. It's a pure element. E is a mixture of a compound and elements. So that one can't work because the question is asking for two elements. So the one that fits best is the gas. Because remember, all mixtures, gaseous mixtures, are homogeneous without exception. So what do we have? Well, it looks to me like and you can see that D is not homogeneous, right? You can count these clear ones, and then you get a colored one, and then you get two clears, and then a color, and then a clear and a color. So they're not homogeneously mixed. Anywhere you sample, you're going to get a different composition. So I think probably and remember my rule, if one doesn't seem to be fit your idea of the answer, pick the best one. And since we don't have any of all of the above or two of the above or none of the above, then you got to pick one of them. And the best one that refers to elements as a mixture that's homogeneous is this gas. Okay, which represents the homogeneous mixture of an element and a, okay, I'm going to have to shrink it, sorry. Let's go back down to maybe, okay, there we go. An element and a compound. So you need to have an element and a compound, nothing else. Compound here, element there, those don't work. This one's not homogeneous, we already decided that. Besides, there are no compounds there. So here we have an element that's a square and a compound that's two circles, one dark and one light. So E is a homogeneous mixture. And all you have to do is take a sample size, right? Here we have two elements and two compounds. Here we have same. Here we have two elements, two compounds. Anywhere you sample, you get the same composition. So 13 would be E, which represents a solid element. All right, we determined that B looked like a solid, and it's an element. So that one fits the definition quite well. It's the only pure one in there. So that's your best guess for, would be B for 14. All right, let's see. How about this one? Let's say all of these compounds are in an aqueous solution, which is incorrectly named. So all of them are named correctly except for one, because test taking technique, there are no one of the aboves, two of the aboves, none of the aboves, that type of thing. So only one of them will answer the question, which is incorrectly named. So that implies that all of them are named correctly except for one. And they're all acids, right? See that hydrogen in front? One or two hydrogen acids, that one's got three. Those are all acids. So we had acid naming convention. So what is the acid naming convention? What's the first rule in naming an acid? Actually, it'd be the second rule. We already named the first rule. You got to determine that it's an acid. So you look for that leading proton. Once you've determined it's an acid, then you say, is there oxygen there? Is there not oxygen? If there's no oxygen, you say hydro. If there's oxygen, then you don't say hydro, right? So you look for whatever is connected to the hydrogen. In this case, the sulfate ion. And remember, when you name an acid, 8s become X. So sulfuric acid is correct. The next one, the carbonate ion. 8 becomes X. Carbonic acid, that's correct. Phosphoric acid is correct. Phosphate, 8 becomes Ic, right? So for the first three are correct. How about this one? No oxygen, so we started with hydro. That's correct. We're starting with hydro, and then we change, instead of chloride, right? If this were a gas, HCl would be hydrogen chloride. When you dissolve it in water, then it becomes your acid naming convention. Hydro and the chloride becomes chloric. hydrochloric acid. That one's correct. HCN. It needs to start with hydro. This one does not. So that means E is wrong. So how would we name it? We would say hydro, and then the cyanide ion is a polyatomic, and the final exam is going to have all of those useful information tables that you've seen throughout the semester. They'll all be on the final. So if you can't remember the polyatomics, then there's a table there to show you what they look like and what their names are. So the cyanide ion, Cn minus, I becomes ic, just like chloride becomes chloric. But we need to precede it with a hydro. So it's hydrocyanic acid is correct. And to answer the question, E is the one that's not named properly. How about this one? An easy one for a change, right? Believe it or not, there were some people that missed this one. So this draws attention to the difference between accuracy and precision. So what is it? What do you have to have to be accurate? You have to either have a true value that you're aiming for, or an accepted value that a group of people have decided this is our target. You need to have a bullseye. So in order to be accurate, the average of your measurements needs to center around the bullseye. Right? So 3 would be accurate. Believe it or not, 1 would be accurate also, because the average of these measurements puts the value close to the bullseye. But number 3 is also precise. Precise refers to grouping. When your measurements are grouped very tightly, very close to the same values, then that is precision. So 3 is both high accuracy, high precision. Whereas 2 is high precision because of the grouping, but low accuracy because they're nowhere near the bullseye. And 1 is high accuracy, but low precision because the group is spread. Now, of course, we're missing 1, right? We're missing 1 that talks about low precision and low accuracy. So if you move this grouping off to one side, then you would have low, low. All right, now let's look at the question. Which of the following figures represent a result having low precision, which means poor grouping? The only one that shows poor grouping is 1. So that's why the answer is A. Okay. I'm not sure how far along I'm getting, but I'm going to just keep chugging along. Okay, similar topic. The amount of uncertainty in a measured quantity is determined by what? Well, let's see what our options are. We do have none of these, and we have both, and we have neither. So they're referring to A and B. So the amount of uncertainty in a measured quantity is determined by what? Well, the instruments could be faulty, right? They could give you a false reading, give you an uncertain value. You may be able to measure what that uncertainty is, or you may not. Right? It may be a systematic error that you can nail down and compensate for, or it may be a random error that cannot be compensated for. So the limitations of a measuring instrument, one possibility. Yes, that's true. Uncertainty is produced by your instrument. The skill of the observer, that's also a problem. That's why when round-robin check samples are sent to different labs, each lab could have exactly the same instrument, manufactured on the same day by the same company and maintained by that company within very narrow limits of precision. And you still get wildly different answers. In that case, you know that your sample is subject to the skill or the lack of skill of the observer. Right? So both of those are possibilities. So both the skill of the observer and limitations of the instrument are instrumental in introducing uncertainty to an observation, any measurement. So that's why C is the answer to this one. Oh, which of the following of these are incorrectly paired? Remember, we have certain groups, the verticals, in our periodic table that have names, right? So let's see, calcium, alkaline earth metal. That's true. This is just pure memorization. So second group, calcium is in that group, alkaline earth metal. V stands for vanadium, not for vengeance. Vanadium. Vanadium is right here. Third one over in the transition metal group, scandium, titanium, vanadium. So vanadium is a transition metal. That's true. B is also true. Cl is chlorine. It's in this group, the halogens, right? That's true. It says chlorine halogen. H, noble gas. Where is H? Well, H doesn't fit anywhere, right? H doesn't fit in any group. It's special. It's just hydrogen. We put it on this side of the chart just to balance helium, because helium is definitely a noble gas, but hydrogen is not an alkaline metal. It just sits out here by itself and does its own thing. So hydrogen is not a noble gas. That's false. The last one, U, is for uranium. Uranium is down here. Let's see. Yeah, you can see that. Uranium is down here. Yeah, here it is. It's in the actinide series, right? It shoves right in here next to actinium. Is where it would go in the periodic chart. So the only one that's wrong there is hydrogen. Let's see. Now we're talking about distinguishing between chemical and physical changes or properties. So the boiling of water, we're talking about a process here, is demonstrating what? Is that a chemical change or a physical change? How do you tell the difference? A chemical change actually changes the nature of the reactants. In other words, the products are entirely different than the reactants. With a physical change, usually all you're changing is the state of the element. And you can restore the element or compound, excuse me, the substance. You can restore the nature of that substance to what it was before just by reversing the process. So the boiling of water could be reversed by the condensation of steam or water vapor. So what is this? Let's see, physical change, yes. A is possible, B is possible, that's it. The rest of them can't be because they mentioned chemical change. So we have to decide between A and B. Physical change because the water merely disappears, or physical change because gaseous water is chemically the same as the liquid. That's the best answer. Just because the water disappears doesn't mean that it's a physical change, right? Because if the water disappears, it could disappear because you have electrolyzed it and converted it into hydrogen and oxygen. That would be a chemical change. But the boiling of water simply changes state from liquid to gas. That's why B is the answer for 46. Okay, now we're looking at the structure of the atom and production of ions. So in this one, we have 10, SN is 10. With a mass number of 206. So what does the mass number mean? Mass number is the summation of the number of protons, the number of neutrons. Okay. So if you know how many protons there are, then you can find out how many neutrons there are. Right? Just subtract the protons from 206. Can we find the number of protons? The answer to that question is a resounding yes, because we have the symbol. We know what the element is. 10 on your periodic chart, it's right down here, and it has an atomic number of 50, which is the number of protons. So we would put 50 here, or you would put it on that blank right there in your chart, then subtract it from 206, right? And you would get 156 neutrons. Okay? How many electrons does it have? The answer to that question is, first, how many protons are there? And is it ionized? If it's not ionized, if it's a neutral element, the number of protons equals the number of electrons. In this case, it's not ionized. So the number of electrons is 50, just like the protons. And what's the charge? Well, all you have to do is look at the symbol. There's no charge. Plus, we just said that the protons and the electrons were equal, so the charge is 0. Okay? Next one. The symbol is blank. So what is the symbol if we know the number of protons? Go to your periodic table. 35 protons will tell you exactly what element you have. Let's see, 35. Right over here to bromine. So bromine has 35 protons, just like it says. The number of neutrons, if we're going to give it the same symbol, similar to the 10, we need to know the mass number. 35 plus 40 is 75, right? So that will be your symbol, well, without the 35. Now, is there a charge? The number of protons is 35, the number of electrons is 36, which means what? There's an imbalance. You have one extra negative charge because of one extra electron. So the charge is 1 minus. And that means the symbol would be this with a minus. Okay? Iron 2 plus. Now we got an ion here. But first, how many protons does it have? Well, we go to the periodic table. This is your best friend. 26 protons. Right. So 26 protons. And the mass number then would be 26 plus 29 is 55, right? There you go. Now, you were already given Fe2 plus without the mass number, but I'm just filling that in to be complete. You only have to put answers in the spaces that are given, so that's not an issue. But the number of protons is 25. The number of electrons is how many? Well, we have a charge. The charge is given as 2 plus, of course. You can see that from the ion. So what does that mean for the number of electrons? We have a deficit of 2 electrons. So if we have 25 protons, we need 2 less electrons, which means 23 electrons. Okay. So 23 electrons. Now, why are we changing the electrons and not the protons? Because if you change the protons, you have a different element. You cannot mess with the protons. If you want to charge electrons, that's your only option. Okay, we got some compounds here to name. We'll go through these rather quickly because I want to try to get halfway if possible. All right, so CF4. What type of compound is that? Is that naming convention 1, 2, or 3? You look for where the elements came from. Carbon is a nonmetal, fluorine is a nonmetal. Type 3, so we say carbon, tetra, fluoride. Okay? Now this one might be a tricky one. Lithium and hydrogen. Lithium is a metal, and hydrogen's its own character. But it's definitely not a metal. So we would use the metal, non-metal, type 1 or type 2 convention, and then we decide which is which. Well, if we've got a metal from, lithium is in the, is an alkali metal, first group, fixed charge, type 1. So we only have to say lithium hydride. Remember, the anion position in a name receives the IDE ending. How about COI2? Oops. Little o. What type is that? Well, it's a metal, non-metal, so it's a 1 or a 2. Then we have to say, what is cobalt? Where does cobalt come from? Cobalt is a transition metal, right? It's right here. So that means it has the potential for multiple charges. Now, while I'm on this topic, now we're going to get that, excuse me, we're going to get to that one in the next one, AgCl. So let's finish cobalt and iodine. So we're going to have iodine has a -1 charge because it's a halogen. So it has a total of 2 minuses. So that means cobalt has to be a 2+ charge because the compound is neutral. So now we have cobalt 2 iodide. It gives you only the information you need to write the compound, no redundancy, and unambiguous. There's no other possibility for this one except that. Now for the next one, AgCl. Now, this is either a type 1 or a type 2. Silver is a transition metal, but if you look at your periodic table, silver only has 1 possible charge, a 1+ charge. So you could, theoretically, name it with a type 1 convention. Silver iodide, silver chloride, excuse me. Silver chloride. And there are a couple of other metals in the transition group that would follow this convention. So that's correct. But for our purposes, I've told you before, and I will accept the charge on silver, just so that you don't have to think about anything. Say, if it's a transition metal, okay, it's type 2. End of story. Go ahead and name it that way. That's fine. Either way is okay for me. Now, if you take another chemistry course, be sure that the instructor thinks the way I do, or figure out what that instructor wants. Okay, let's see. N2O5. What do we have here? A nonmetal, which means we say how many nitrogens? Dinitrogen, pent oxide. We don't say pentaoxide. Drop the A, make it sound better to the ear. Pentoxide. Okay. How about the last one? NH4, NO3. What you need to recognize there is you have a compound that's made up of polyatomic ions. Polyatomic ions have fixed charge, always. One polyatomic ion has a charge, nothing else. It may have a neighbor in that family with a different charge, but they're each different from each other. So in this case, ammonium is the cation position, and nitrate is the anion position. And since they both have fixed charges, we use the type 1 convention. All you have to say is ammonium nitrate. That's it. You're done. Okay. Write the formula for the following. The key to writing a formula is the reverse of what we were just doing. You decide, is it a metal, non-metal, or is it, in most cases, a metal with a polyatomic ion, because all the polyatomics we have studied are anions, except for ammonium. So this one, the first one, magnesium hydroxide, is a metal with a polyatomic ion with a fixed -1 charge. Hydroxide is this. Magnesium is this. Magnesium is a fixed charge metal. So we need to balance the charges. Polyatomics cannot be split up. If you put a subscript in here, like a 2 and a 2, to make that two minuses, you're wrong. OH is a polyatomic ion that you cannot mess with. That's the only way to get 2 polyatomics out of this arrangement and balance the charge. 2 minuses, 2 pluses, there it is. Dibromine heptoxide, you just have 2 bromines and 7 oxides, 7 oxygens. Right? I don't even need to write that one down there. Magnesium 4 oxide, type 2 compound. Magnesium 4 means it's 4+ charge. Manganese, excuse me. Manganese has a 4+ charge, and it's paired with oxygen, which has a 2- charge. So how do you balance it? You need 4 minuses, which means you need 2 oxygens. So it's MnO2. Sulfurous acid. So when you're going backwards from a name to the compound, you need to know where the name came from. There's no hydro in this name, sulfurous acid, so you know that it has oxygen in it. Sulfurous, us's are derived from X become ick, no, excuse me. Eights become X, so sulfate would be ick, but sulfite would be us. So the sulfite ion is that one. That's where the sulfurous comes from, sulfite. Then it needs its acidic hydrogens in front, which are each a +1 charge. So it means you need 2 of these. So H2SO3 is the correct formula for sulfurous acid. How about acetic acid? There's no hydro. So we look at acetic. Where did it come from? Ics are derived from ates. Ates become ics. So acetate is the source. That's the source of your polyatomic for this acid. You only need 1 hydrogen. So that's acetic acid. I've drawn it other ways. You can draw this part right here as like that. Then you would put the hydrogen out here. So I'll accept either one. Nitrous acid, right? No hydro. So we're looking for a polyatomic more than likely. If you have an oxygen and 3 or more elements, you definitely have a polyatomic. So nitrous, us becomes from ite. So nitrite is the source here, NO2 minus, with 1 hydrogen. HNO2 is nitrous acid. Okay, let's see. We skip a lot of them to get to, some people miss this one. What's an empirical formula? Well, these are representations of molecules, right? So the molecular formula would be just to count up all the elements and write the formula from that, right? So the first one would be 1, 2, 3, 4, 5, 6. 6 carbons. How many hydrogens? 6 hydrogens. Okay, that's the molecular formula. What's the empirical formula? The empirical formula is the simplest whole number ratio. What can you divide into both of these numbers that will give you the simplest number with no other divisors? Divide 6 in there and you have 1. That's the empirical formula of that compound. Okay, you can do that for the other 2. Time short, I'm not going to spend time on those other 2. Let's see. Okay, now we're getting into discussion of gases. Let's see. Yeah, there's enough room there. What's a manometer? A manometer is a device for measuring the pressure of a gas in a sealed container. Right. So let's look at the question. What is the question? What's the pressure of the sample of gas inside the vessel? Right. So we have a vessel with a volume of 2.34 liters. .34 liters. There's a gas in there, right? And the question is, we want to know the pressure. What's the pressure inside? So we connect it to a manometer, and the manometer is contains mercury in it, and it's open-ended to the atmosphere. Okay. So it's going to go like this, and then it's going to go down. Like that. Sometimes it helps to draw a picture. It's got mercury in it. We don't know where the levels are yet. That the problem tells us that. So the mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the arm open to the atmosphere. So that means it's going to be lower here and higher there. Right. So the distance here is 24.3 torr. What's a torr? A torr is a millimeter of mercury, right? 24.3 millimeters of mercury. So the atmospheric pressure bearing down on that column is also taken into account, because not only is the difference in mercury height pushing on the gas, you've got atmospheric pressure pushing down here. And it's what? 1.23 atmospheres. So what is the pressure in here? The pressure in here is enough to push down on this mercury and against atmosphere. So you need the total of this one plus the total of that one to tell you what's inside. But you can't add apples and oranges. You can't add atmospheres and torr. So, test-taking technique, what's the unit of measure for the answer? Torr. So you wouldn't convert this one to atmospheres, you convert that one to torr. Right? So how do you convert atmospheres to torr? 1.23 atmosphere. You need a conversion factor. Right? So how many torr in an atmosphere? The standard is 760 torr. 760 millimeters of mercury. Same thing. So we multiply 760 times, see, here it is. 760 times 1.23. And we get 934.8. 934.8. And that's torr. We add that to 24.3. 959.1. Torr. Okay, so what's the best answer? Well, the best answer is the closest one to 959, which is E. Okay? All right. So what's next? Complete the following. Because real gas particles have attraction for one another, which is true, one of these statements is either true, or since E says at least two of the above statements is correct, we have to look at all four of the above and see, are there two that are correct, or is it just one? Real gases act most ideally at standard temperature and pressure. So what was the rule? High temperature, low pressure. Relative to what? High temperature is relative to absolute zero. So 273 K is high temperature, or 293 K, which would be, or 298 K would be 25 degrees centigrade. So that would be high temperature. So standard temperature would be true. Well, actually, standard temperature for gases is zero. So that's 273 K. Pressure. Standard pressure is 1 atmosphere. Is that high or low? That's low pressure. Compared to what? Well, compared to 50 or 60 or 100 or 200 atmospheres. Right? So A is true. Real gases act most ideally. Well, let's see what else there is. Because actually they're more ideal the lower the pressure and the higher the temperature. B says we assume gas particles have negligible volume. That doesn't have anything to do with their attraction, because with their attraction, it's only with the atomic nature. So B doesn't work. 1 mole of an ideal gas at STP has a volume of 22.4 liters. That doesn't say anything about why real gases behave the way they do. Real gases act more ideally at higher temperatures and lower pressures. Okay, so we could say that the key to discerning whether it's A and D or just D is, what do we mean by most? Real gases act most ideally at standard temperature and pressure. No, they act most ideally when the temperature is very high and the pressure is very low. So they become more ideal if we increase the temperature way up and decrease the pressure way down. So actually the best answer for this one is D, high temperature and low pressure. Okay, we got 3 minutes left before we have to call it a day. Let's see, everybody remembers this one. What are these values? If you have a 1 liter bulb at standard temperature and pressure connected to a bulb that's evacuated, you open the valve, what happens to these values? I mean, are they equal to 0, greater than 0, less than 0, or not enough information? Well, it should be obvious by now that delta H, Q, W, and delta E for this situation are all 0. Let's see if I've gotten far enough. Okay, we can do this one in the last couple of minutes we have. This goes to the definition of enthalpies of formation, or heats of formation. So how do we tell the heat of formation for CO? First of all, we start with the product, CO, and the product at standard temperature and pressure. Carbon monoxide is a gas at standard temperature and pressure, so that's true. There's 1 mole of it. That's fixed, can't change it in this situation. The delta H, little 0, which means standard temperature and pressure, of formation for this gas depends entirely now on what we do with the reactants. So the reactants have to be elemental for each of the elements in the compound. So we need carbon and we need oxygen. Okay? But they have to be at standard temperature and pressure also. So what is carbon at standard temperature and pressure? It's graphite. So carbon, oops, there's 1 of them. There's 1 here, 1 here. We're good there. Oxygen, though, at standard temperature and pressure, is a gas and it's diatonic. So how many of these do we need? We only need 1/2. So which one matches that? It doesn't matter what the delta H is. To answer the question, you just look at the form, right? You only have 1 CO on this side, so that means B is possible and C is possible. So you look over here on this side, carbon's the same, but oxygen is different. Oxygen at standard temperature and pressure here is not a single atomic. So this one tells you the answer. C is the answer to that one. So there looks like there's a lot of information that you don't need. What you need to know is, how do I write the reaction for the heat of formation for any compound? You start with the compound and work your way backwards. Okay, it looks like our time's up. And what I've got to do is say, we'll pick it up here on Thursday. And in the meantime, you can be looking at your old exams for things that you don't understand or become dim. Study up on them. Bring your questions to the Thursday meeting. And before I pick up here, I'll field questions first. Also, you need to be thinking about your labs. Some people are catching up with their labs. Some people are not. And since these are two separate courses, 101 and 103, you could pass 101 and fail 103. That's just the reality. I don't integrate the two. If management wanted them integrated, they put them both together under one course number. But since they don't, I grade them separately. Okay, so I'll see you on Thursday, same time, same station.